So here, let me try something else. Okay. Let's get that ready. Well, hi everyone. Thanks for coming. Sorry for the technical delay. My name is Jim Leonard, and if you remember me from the demo scene, I was called Trickster, and I was in the demo group Hornet. If you might also know me, if you're not familiar with the demo scene, as the co-founder of MobyGames.com. But I'm not here to talk about either of those things. I'm here to talk about a waste of time I did in 2004. And it's called 8088 Corruption. It's to display full motion video on a really old, slow machine. So I was going to ask how many people have seen it by show of hands, but I think I'll just go ahead and show it to you. I apologize for the colors. They're probably going to be a little bit off because of the camera and everything. All right, well, okay, now it's starting to come back online here. Let me see if I can fire this up again. Ah, darn. All right, I should show this to you just so you can get an example. Let me pull the video real quick. All right, which one is it? This was supposed to play in the presentation. I think it's this. No, it's no video codec. All right, let's try one more time. All right, well, it was probably embedded into the presentation, for which I apologize. All right, well, what you're supposed to be seeing is a black and white video of footsteps moving and a 24-bit color of footsteps moving, but because the 24-bit, they both take up the same bandwidth. They both take up the same amount of disk space, memory space, whatever. But because this guy is going at 60 frames a second, you can actually tell it as footsteps walking, whereas the 24-bit color one, it almost looks like someone is just stamping up and down in place. So this is what I mean about frequency. More samples is better. So in trying to solve this problem, I started out with what looked best. I did some empirical testing and took full motion video, 60 images per second, not stuff you grab off of YouTube, because that maxes out at 30. I actually filmed stuff myself and converted it to 60, created integral divisions of that, 30, 20, 15, 12, et cetera, frames per second. Came up with 30 frames per second is the minimum acceptable quality to call it motion video. And then did the same thing for audio, and I came up with the result. 22 kilohertz is just about acceptable for something like music, and that's what you just heard. So and then we moved to the output device. To determine what was possible, let me give you a small history of CGA here. CGA is a memory adapter that has a little bit of RAM on the card, and it is constantly scanning that RAM, and whatever is in that RAM is what's displayed on the screen. So essentially, however fast we can update that RAM is how fast we can change the contents of the screen. So some more empirical testing. I wrote a small assembly language routine that measured how fast the CPU can actually move data into the CGA adapter RAM, and came up with 160K of data per second moving to the CGA card. So now we take all of our results and we figure out what's possible. We found out that moving data CGA tops out at 160K, 30 frames per second is our minimum acceptable quality. Audio 2, so we subtract the audio from how much memory we can move into CGA, and we get 4.6. So our final result is 4.6K is the maximum amount of RAM we can copy each frame to stay within our 30 frames per second target. So when we research the output device, what are our options? Well, graphics modes use 16K. That's greater than 4, so that's not an option. 80 by 25 text mode uses 4K. However, 80 by 25 text mode has a problem with snow. And if this sucker boots, I'll give you an example. When you write direct, the memory in CGA is not dual ported. So when you try to write directly to screen RAM, I don't know if you can see it. See how there's snow? There's all this flashing snow on the screen whenever the screen's updating. You can't use that. The video would be unwatchable. So we have only one mode left, and that's 40 by 25 text mode. So that's our final result. We have to, whatever we're going to do, if we're going to solve this, it's got to be in 40 by 25 text mode. So how the hell do you convert images to display in 40 by 25 text mode? The converter went through 3 different iterations. One was a resolution-centric approach, which was very naive, and you'll see why in a second. The second was I tried to attempt some dithering or half-toning, and that had pluses and minuses. And finally, there was a brute force linear time comparison, which worked the best. So let's give you some examples of this. The first idea was to emulate character graphics. I don't know if any of you are familiar with like the old CX Spectrum or anything like that. The Spectrum displays graphics that are actually made up of 8 by 8 tiles. It's actually the character generator. It's text mode, but it's like a custom font. I'll have an example in a second. So I was thinking 40 by 25 text mode uses the same thing. It's 8 by 8 character cells. So only 2 colors are allowed per cell. And if you count out all of the individual dots that are actually displayed on screen, it comes out to 320 by 200. So this was my reasoning, that I would start with a 320-200 picture and try to map it as best I could to all the dots on the screen. Here's what ZX Spectrum stuff looks like. If you look at the zoom in on the leg, you can see it's kind of blocky, and if you go ahead and break it out, my idea was to emulate that. And the difference between the Spectrum and the IBM is that on the Spectrum, you can change all of those pixels in each block. On the IBM, you can't. So this was the basic conversion. Remap colors using the 16-color palette, determine the two most popular colors, remap it again using just the two colors, and compare to all possible character and color combinations and use the best one that matched. And I figured it's got graphics characters, it's got lines, it's got shaded characters, it should work, right? Well, the initial results weren't that great. I'll give you a second to look at those. These were the test pictures I used in determining everything. I was happy to see that some stuff was a perfect match, which makes it look almost as if you drew it in that mode. Well, not really. But obviously the biggest cons were that since entire areas were mapped to a single flat color, the colors were not only wrong, but they completely obliterated all picture detail. So as a knee-jerk reaction, I went completely the other way. I figured, okay, well, forget about trying to match resolution exactly. Let's just look at color. Halftoning, or dithering, depending on how you use it, is the process of trading spatial resolution for color resolution. And the IBM character set includes a 50% on-off checkerboard character. And I figured if I use that, I can try to simulate a crude form of halftoning and come up with different colors. So there's the shaded characters up there. The 177 is the one that I used. And by using all of the colors and eliminating duplicates, you can get a fairly reasonable facsimile of more colors. So that one was really easy to do. I just compared the process was resampling the 320-200 picture down to 40 by 25. So I had exactly one pixel to one character pixel lookup to do. And you resize it, and then you use the closest match. Well, the colors are better, but it looks like ass. I really almost submitted this to Pilgrimage. I'm glad I didn't, because the colors were better. Because the text character is also 177, I had less memory to fling around, so I could have probably done even faster updates to the screen. And the conversion process is really fast, but the con was big enough that obviously I did not. So at that point I was stuck, and this is where my collaboration with God Jr. really came in handy. I had mentioned something like, if only we could get results were halfway between these two. And he suggested an idea that led to the idea that was used in the final converter, which is resampling both the picture and the character set to be paired bilinearly down by 50% so that they smooth out. And I'll explain this in a second. So, well, as I just said, you still take the same 320 by 200 picture, resample it 160 by 100 smoothly. You don't drop pixels. You use a bilinear resize so that it gets all kind of smooth in the process. It aliases in the process. Anti-aliases, rather. And then divide that up into 4 by 4 cells and compare each of those areas of the original source bit. Similarly resized character color combination in the character set. You resampled that as you compared as well and used the closest match. And that obviously had the best results. Now, the projector the gamma is a little off, so I apologize for the dark areas in the clown, but at least now you can see that the colors are better. You can see that the dark outline around the cloud's eyes, and so forth. So the pro of this, obviously, is that detail and color is preserved probably as best it can in a linear search, which leads to its disadvantage. The conversion process is so slow it can be measured in seconds per frame, which sounds crazy considering that, this is the conversion wasn't done on this machine. Trust me, this is like on a Pentium 2 gigahertz. It takes seconds per frame because you have to do all those comparisons to get your final 1,000 characters. It's over 1 billion comparisons per frame. So why did this third process work best? Mainly because the checkerboard character, when you also resize it down bilinearly, 50%, the pixels blend together. And those blended pixels become solid colors, and they match better with solid areas in the source bitmap. And because the characters are resized at the same ratio as the bitmap that they're being compared to, you can still get these perfect matches, which preserves detail. So that's the converter, but the converter is only half the story. It is only 40 by 25 text mode, so in order to, how do you win a wild compo with something written in text mode? You have to choose your source material very carefully. I mean, the stuff that you saw in the demo was not by accident. It was very deliberately chosen. As I mentioned before, the human brain works best with familiar patterns. It needs a lot, well, it needs a lot of information to make matches, but familiar patterns obviously would be better. So faces are good. Learning how to recognize faces ever since you were born. Human movement, like walking or dancing, is also good. Try to avoid complicated backgrounds, tiny details, stuff that isn't important to the focus of the material that you're trying to present, that is just going to give the converter a hissy fit and trying to figure out what to choose. And finally, a little social engineering never hurts. I knew that my audience at Pilgrimage would be full of demo sceners, and I figured Tron would be a pretty good thing to show that people would recognize. So what I'd like to do is give you yet another example, if I can get this functional, of how important it is to choose source material. Camera's what? Oh, shoot. Hold on a sec. That's not good. Okay, there we go. Speed this up. Hold on a second. Okay. So again, this is an example of how important choosing the source material is. This didn't convert well. It's complex characters. It's a lot of dark stuff, which unfortunately this monitor is not very good at reproducing. But because it has faces, human movement, and is an easily recognizable pop culture reference, I'm sure you guys are going to be able to figure out what it is.
I repeat, we are under attack.
Careful. Audio helps too. Damn. It looks better on the monitor if you can see it here.
Help!
Only human.
Dodge this.
Over an hour. All right. So again, that was probably a pretty bad conversion, but at least you could tell what it was. I was going to talk a lot about the player, but I'm really short on time, and to be honest, there's not that much to the player. This is the surprising part. When they saw this, they thought that all of the heavy lifting was in the player, that it was some, physics-defying assembler that I had written or something. And as you just saw, most of the heavy lifting is done by the converter. The player is very simple. It fills up as much RAM as it can with audio and video data, and then starts the playback and divides into two code segments. One is a main code, which tries to just constantly keep loading off of disk and keep the queue full. And the other is an interrupt handler that at the desired frame rate frequency sends code pulled from, sends data pulled from the queue to the CJ frame buffer in the audio. And that's pretty much it. If the queue can't stay filled, like you've got too high a frame rate or your hard disk is too slow, the main code will pause playback until it's full again. Now, so far you haven't seen any rebuffering. There's a final example I'll have later that does rebuffer. You'll see that in action. The whole player was engineered with the idea of how to maintain audio-video sync. Nothing pisses me off more than watching a video and slowly having the lip sync drift off, either forward or backward. So I knew, again, to complete the illusion, the audio had to stay in sync, or it would have looked really shoddy. So I store the data in chunks, and each chunk has a frame to put on screen and the audio to display for that frame. To get the right timing, I set the sound card's audio buffer to the length of that frame. The nice thing about sound cards for even as old a machine as this is that when sound is done playing, it fires off a hardware interrupt. So the hardware interrupt handler that I wrote updates the next audio buffer and at the same time slams the next frame up on screen. So the sound card is driving the entire system. The CPU is not even involved there. And as a result, since every frame is locked to the next piece of audio that's going to get played, it cannot get out of sync. Some people have compared 8088 corruption to a lot of things, some of which you can see up there, ANSI animation and things like that. I never understood the ANSI comparison. It's not ANSI animation at all. It doesn't use ANSI sys in any way, even though it certainly looks like it does. ANSI art is painstakingly crafted by artists, and if you're not familiar with ANSI art, I suggest you go check out Radman's talk, which I don't know what it is, but go see his talk. He's going to talk about ANSI and ANSI artists and things like that. And artists almost always produce better results, so I never understood the comparison. If there are any video compression geeks in the audience, you could compare what I just showed you to a vector quantization codec that uses a fixed codebook, the codebook, of course, being the CGA ROM font and all of its character combinations. But it's not really a codec because there's no actual decompression on playback. It's loading completely converted frames off of disk. Not only that, but I didn't start with a traditional codec like Cinepac or DivX and try to port it backwards to work on something slow. I started with the hardware's requirements first and went forward and saw what I could do with that. So I consider it more transcoding than actual compression. And another comparison is, people have accused me of using AAlib or libcaca, monotext module of libggi. These are C libraries that started in Unix and eventually got ported to DOS and Windows that convert graphics into text. But they use a completely different method. They're meant to be real-time conversions, something you plug in. There's like versions of VLC and Zinni and other Unix players that can play video through these things. Why you would want to do that, I don't know. And they don't produce as good a job because they're terminal agnostic, meaning they don't have access to the actual text data, the font data they're using. So they have to come up with a generic table of what might look good in grayscale, which is the AAlib example on the left, or the same thing in color, which is that's a libcaca example, actually. So how can this thing be improved? Everything about it can be improved, actually. Nothing's correct on the first try. The player itself updates this. Since the sound card is slamming video to CGA RAM whenever it wants to, there's shearing. So on the scroller probably didn't look very smooth, and it might have torn a little bit. That's because it updates whenever it wants. Since the sound card interrupt is driving the whole system, the system timer tick interrupt is actually free. You could use that to simulate a vertical retrace interrupt. And instead of writing directly to visible screen RAM, you could write to off-screen RAM and then do a nice clean page flip. You could also probably use EMS to buffer, but I consider that cheating because I don't know anyone other than myself who still has an EMS board in a machine like this, so I didn't implement it. Again, unfortunately, this is supposed to be playing. I don't know why it's not, but video preprocessing could have helped as well. One thing that shatters the illusion a little bit is that this doesn't change very much at all, but it does change slightly. The problem is that it leads to these massive changes in the converted output. So preprocessing the source for video noise, temporal video noise, would help eliminate that spark. You could also, if you've got decent temporal noise filtering and or your source doesn't move very much, you could start to do actual compression. You could compare the later frames to the previous frames and only store the changes between them. And then if you can write an assembly routine that can update the frame with just those changes at the same rate or faster than a full move, you can achieve actual compression. Now, if you combine preprocessing temporal noise and compression, you can try to achieve the holy grail of 60 hertz screen updates. This is double the frame rate you get off of videos off of Google Video, YouTube. If you can update the screen at 60 hertz, there's a lot of extra stuff that you can do. It's technically possible right now, but there are some caveats. You're updating 4K per frame instead of, well, you're updating this is actually a mistake. You're updating 2K a frame, but at twice the rate. And at that rate, the CPU is spending more time updating the buffers than it is actually loading from disk. So it is actually currently impossible to avoid rebuffering. You'd have to implement less data rates, like I mentioned before with compression or something. Or you'd have to cache the entire thing to EMS, which, again, I consider cheating. However, just to give you an example of how eerily realistic it looks like, I have an example. Let me do this real quick. This will rebuffer. So it'll pause 3 times when it plays. Again, I apologize. Oh, uh-oh. Did I lose this again? Hold on a sec. If it's not recording, it shuts off. Okay. Again, if you can see the monitor, the colors are more accurate. So if you can see it, I stress you to take a look at that. So what you get with 60 Hz is eerily realistic motion. The video is real cheesy, I warn you.
Pop, pop, pop music. Pop, pop, pop music.
Not that, this part. Whoops. So, autofocus. So anyway, that's that example. "60 Hertz motion, as you just saw, is very close to the limit of the brain's ability to actually discern individual events in time. So it's eerily realistic. Again, if you can avoid the rebuffering issues, because that pretty much kills the illusion. Another thing you can do, if you can update the screen 60 times a second, is that you can actually get a better conversion. Hopefully the image on the right looks better than that on the left. If you keep track of errors during the conversion, you can push them forward. You can dither them forward in time, much like Floyd Steinberg dithering tries to distribute errors left and right on the line as it scans down. And so you can create a second frame to be mixed with the first one that fills in the gaps in the error in the original conversion. And since the screen is updating 60 a second, it's fast enough that they kind of blend together. And so you get a result similar to the image on the right. Hopefully it looks a little bit better. If you look at the color gradations of maybe above his eye, the eye is rounder, for example. So you can pull that. If you wanted more resolution, you can also tweak CGA into a 50-line mode, where the first top 4 scan lines of each character is displayed instead of all 8. This doesn't give you any additional resolution. You don't get more resolution from this, but you do get more flexibility in choosing matches. So you can try to get a more higher res thing there. No, it displays the first 4 rows and then immediately switches to the next row. So what did I learn, and hopefully what can you take away from this, if anything? Know your output device. Having a goal makes it interesting and engaging. I specifically said 30 frames per second on this piece of crap. And so if you stick to that, I mean, that was the goal. That was the challenge to keep going. And again, if you're trying to do something like video on a low resource, this is the same thing with demos too. If you want to write a demo for a low resource platform, focus on the specs of the machine and work backward from them. Don't try to start with an existing code you have for a 386 and port it. It's not going to be applicable. And know your audience. Know your input device as well. Know your audience and experiment. And challenge yourself, because stupid ideas are, for some reason, usually the most interesting to work on. I was going to talk more, but I'm afraid I'm out of time. No? Actually, I've got a little bit more. Okay. All right, now I'm going to gripe. About 9 months after 88, this is extra, after 9 months after 88 Corruption was posted to Google and YouTube and viewed nearly 50,000 times, VH1 started showing these classic bumpers meaning like a piece of video you display between program segments or something. And it showed a PC of old vintage showing video mode with a cheesy MIDI soundtrack. It may have mostly been coincidental, but of course it caught my eye. Now this isn't going to play, but I do have it. If you want to see an example of what I'm talking about, give me a sec here. Very good. And that's part of my gripe, which I will get to in a second. I hope this works. Oh, you can see it. I can't. It's the overlay. All right, hold on. Let me switch audio sources here for a sec. Let's try this again. The first time I saw that, I thought that was cool. And then after I did, after I thought about it, it actually started to piss me off. Because, okay, hold on, let me see if I get to the next slide here. Okay, well, obviously it's ripping off AAlib. No thought went into it at all. They just ran stuff through AAlib and converted it. The frame rate was unnecessarily low. I just showed you 60 frames per second on a dog shit piece slow machine, and then they've got a better one, and it's only doing 12. And the music was unnecessarily cheesy. General MIDI was bad, but it wasn't that bad. And here's the non-obvious gripes where I show you what an incredible nerd I am. Other things that pissed me off about this is that the distortion was inverted. Notice that the lines are actually thinner in the middle than they are at the end. That means the screen is bending inward, not outward. I never got that. After the whips, there's no sync. It's not a real text mode, for example. Yes, I actually counted the letters. And most importantly, the computer used in the shot, as you notice, was a PS1. That's a 386 with VGA. It's capable of actual video. They could have put up a Spectrum or something like that. Yes? They could have at least turned on the monitor. Very good. So that's about all I have. My email is here. You can download all of it. And after the con, I will have full source code up for everything. And as a perfectly shameless plug, please buy Mind Candy Volumes 1 and 2, which you can get from myself or Andy Voss, who's also in the audience. And that's it. If you have any questions, please feel free to see me. So, and before we go, are there any questions? Yes? Something like this? Well, that was certainly an inspiration. Probably a better thing was, did I look at like any text mode demos or something like that? Well, yes, the girl dancing was definitely an inspiration. State of the Art was one of the first Amiga demos I ever saw, and of course it blew me away. And I someday hope to reproduce that kind of video compression on this thing as well, but one step at a time. No, I didn't explicitly look to try to duplicate it. If I did, actually there was a demo in the late 90s for DOS that did in fact take video output from an emulator of State of the Art and run it through AAlib, and that was it. And that was the demo. And it didn't look too good, as you can imagine. Actually, yes. CGA cannot, okay. Could I have modified the font table to get better matches? CGA does not allow you to do that. Now, if I had EGA or VGA, yes. But if I had EGA or VGA, I probably would have done a completely different track. I would have probably tried to do like the state-of-the-art vector stuff or something along. Actually, sorry. Yeah. No, you. I am pointing at you. Sorry.
Okay. How big are these videos when you're actually compressing down?
Very small. They are minuscule. The Matrix one you saw was over a minute long, and it was, I'm going to have to wait. Okay, it takes about 15 seconds to do a directory listing on this. I apologize. I think it was about 5 meg total. You could load this onto a 10 meg MFM hard disk. It should still play if you have that old a machine. Yes, sorry about that. Yeah, it's 5.4 meg. So they're very small. I mean, each video frame is 2K, so multiply that up by 30 times a second. That's 60K, and then the audio is 22, so it's 82K a second. So they're pretty small. Yes?
How did you get the 5 meg file into that machine?
I have a Ethernet card that magically works in 8-bit mode, so I did that. But before that, I had a parallel cable, and I would do it with fast links. Yes, Andy? Where did I get the music from? For the original one, I shamelessly stole it. It's Goa Trance from the group Space Cat. It's a 2003 tune, and every time I heard it, that middle section, I kept thinking, wouldn't it be great to have that in a demo? So, anything else? Anyone else? No? All right, well, thanks for coming.